Okay, geometry. We're continuing on with our trig section, and we're applying the Pythagorean theorem in a slightly different way to solve sides of triangles. So let's get into it. First of all, in a right triangle with acute angle measure theta, sine theta equals 1/2. What is the measure of cosine theta? So we really need to draw a little sketch. Pick something to be theta. And remember, we have toa. Sine is opposite over hypotenuse. So we have opposite over hypotenuse. So let's figure out what that third side is. Remember ABC. So leg squared plus leg squared equals hypotenuse squared. So I have 1 squared plus b squared equals 2 squared. 1 plus b squared equals 4. Subtract 1 from both sides. B squared equals 3. B equals the square root of 3. And cosine theta is adjacent over hypotenuse. So we have our answer. Adjacent over hypotenuse. Next, in a right triangle with acute angle measure of theta, we have sine theta equals 7 over 9. So sine is opposite over hypotenuse, 7 over 9. Let's figure out what b is. 7 squared plus b squared equals 9 squared, 49, 81. Subtract 49 from both sides. B squared equals 42. B equals the square root of 42, which I can simplify into, I think that will give me 16 times 2. Nope, that's 32. Let's see, 42. I'm going to divide by perfect squares. Let me push pause. I see my problem. There we go. So I have b equals the square root of 16 times 2. So that equals 4 square roots of 2. So we're looking for tangent theta. Here we have 4 square roots of 2. Tangent theta equals opposite over adjacent. So 7 over 4 square roots of 2. I need to rationalize that. So I'm multiplying by the square root of 2 over the square root of 2, and that gives me 7 square roots of 2 over 8. Because the square root of 2 times the square root of 2 is 2. 2 times 4 is 8. Okay, example 1. What common right triangle was probably modeled in the construction of the triangle in figure 2? Use sine of 53 equals 0.8. Okay, so I'm actually going to pull this little triangle out. I have a right angle and 53 degrees. It's just a lot easier for me to see it when it's drawn two-dimensionally versus three-dimensionally, right? So I pulled that out, and I have sine of 53 degrees equals 0.8. 0.8 doesn't help me very much, but I do know that 0.8 is the same as 4/5, because 4 divided by 5 is 0.8. So I can say sine is opposite over hypotenuse, 4 over 5. Let's figure out that third side. So I have 4 squared plus b squared equals 5 squared. 16 plus b squared equals 25. B squared equals 9. B equals 3. So I have a 3, 4, 5 triangle. So it's actually called a right triangle. sorry, it has a pyramid name too, so it obviously is called a right triangle, with side lengths 3, 4, 5. So that's the common right triangle. It's common. I think I get to the question on the next page. A 3, 4, 5 triangle is extremely common. You should recognize it. 3, 4, 5, where I have the legs and the hypotenuse, 3, 4, and 5. At this point, I'm going to point out, if you struggled with that, you could have just kept it sine 53 equals 0.8 over 1, labeling your triangle like that. So I would have my sine opposite over hypotenuse, 0.8 and 1. So I'd have the Pythagorean theorem would give me 0.8 squared plus b squared equals 1. So 0.64. b squared equals 0.36. b equals 6. 0.6, sorry. This is actually equivalent to a 3, 4, 5 if you set up your ratios. 3 to 0.6 gives me 4 to what? If I cross multiply 0.6 times 4, equals 3x. Divide both sides by 3, and I get x equals 0.8. So it's the same triangle, just scaled smaller. Okay, sort of funny. Funny question. The actual angle between the base and lateral faces of the pyramid is closer to 52 degrees. Considering the age of the pyramid, what could account for the difference between the angle measures in part A and the actual measure? Well, the Great Pyramid, they estimate at 4,500 years old. Each block weighs, goodness, several tons. It's conceivable that over time the great weight of the blocks caused the pyramid to settle and shift the lateral faces so the angles are closer. So the weight of the blocks affected the angle. So everything's settled. Why do you think the architects chose to use a 3, 4, 5 as a model for this triangle? It's easy to calculate. It could be any reason. A right triangle with the shortest whole number side lengths. It's pleasing to the eye, honestly, because it's so symmetrical. All right, let's look at the triangle we just looked at with the last problem. So I have theta as an angle, and sine of theta is 0.8. So we just looked at this triangle. Before we were using an approximation, but we don't know exactly what the angle measure is. But we'll assign the angle measure that results in the sine of the angle being 0.8 and just label it as theta, right? So in this diagram, we've got the leg lengths in terms of sine and cosine. So if we have a hypotenuse of 1, I can actually say that this leg length is cosine theta, and this leg length is sine theta, right? Because cosine is adjacent over hypotenuse, and my hypotenuse is 1, and this is opposite over hypotenuse, and my hypotenuse is 1. So the value of sine theta, oh goodness, handwriting sometimes, sine theta equals 0.8, and cosine theta equals 0.6. So I'm just substituting. Instead of 0.6, I'm writing cosine theta. Instead of 0.8, I'm writing sine theta. The Pythagorean theorem states that for a right triangle with lengths ABC, where C is the hypotenuse, the relationship between the side lengths is a squared plus b squared equals c squared. Well, in this case, I can say, sine theta squared plus cosine theta squared. Let me fix this. Equals 1. So this is actually an identity that we'll learn again in Algebra 2, and it's called the Pythagorean identity. We can talk about it in this way too. Let me write in blue. Draw a picture over here. If I have theta, I can have hypotenuse, opposite, and adjacent. I can also say that opposite squared plus adjacent squared equals hypotenuse squared. If I divide everything by hypotenuse squared, because I want to get 1, I have opposite over hypotenuse, which is sine, and I'm writing it in a different way now, cosine equals 1. I have the same thing. Okay, and please note, important, writing it like this is equal to writing it like this, but this one is more acceptable. Okay, that's what we're going to use. Cool? All right. Let's look at example 2. Okay, let's look at this example. Show why tan theta equals sine theta over cosine theta. First, let's try to show what is sine theta. Well, in this particular example, we have katoa. Sine is opposite over hypotenuse, so that's A over C. Cosine is adjacent over hypotenuse, which is B over C. Tan is opposite over adjacent, A over B. Well, let's look at what sine theta over cosine theta gives us. So I have A over C over B over C. Well, when you're dividing fractions, you're really multiplying the reciprocal of the bottom. Those cancel out, and I'm left with A over B, which is the same as tan theta, which is A over B. It's sort of like magic, but it's not, because it's math. So we know, sine that is equal to tangent theta, just to close the loop. So let's try a few. In a right triangle with acute angle of measure theta, sine theta equals 1/2. Use the Pythagorean identity to determine the value of cosine theta. So the Pythagorean identity we just said is sine squared theta plus cosine squared theta equals 1. So I can simplify that to, or I can rearrange it. Cosine squared theta equals 1 minus sine squared theta. I have 1 minus Sine theta is 1/2. So 1/2 squared. 1 minus, when I square a fraction, I'm really multiplying it by itself. So 1 minus 1/4, which is 3/4. So cosine squared theta equals 3/4. Square root of both sides. Cosine theta equals square root of 3 over 4. Oh, 2. Sorry. Because remember, we've learned sweet. Given a right triangle with an acute angle measure of theta, sine theta equals 7/9. Use the Pythagorean identity to determine the value of tan theta. All right, so I know that tan theta equals sine theta over cosine theta. So you know what? Let's just find cosine theta, and then we'll take 7/9 over whatever we find to give us tan theta. Cool. So we know Pythagorean identity. I'm going to use how I rearranged it for the last question. And then plug in what I know. 1 minus 7/9 squared. 7/9 times 7/9 equals 49/81. Phew. So I have 1 minus 49/81. So I really need to change this to 81/81, which is the same as 1. 81 minus 49, 11 to 32. So that gives me 32/81. And we're still at cosine squared theta. So square root of both sides. Cosine of theta equals the square root of 32/9. Show you my work. Remember, 32 is 16 times 2. So we have our answer for cosine of theta. Now, if you go back to the opening exercise, the first thing we did when we solved the triangle using the Pythagorean theorem, you'll see that it's the same answer, okay, for cosine. So the last problem we did. Now let's see if we can get the same answer for tangent. I'm going to go to a new sheet. So we're trying to find tan theta, which is sine theta over cosine theta. The problem gave us sine theta is 7/9. We just solved that cosine theta was 4 square roots over 9. So I'm going to have 7/9 times the reciprocal. 7/9 times 9 over 4 square roots of 2. 7 over 4 square roots of 2. Need to rationalize this or simplify it. Four square roots of 4. 7 square roots of 2 over, this is 2. 2 times 4 is 8. If you go back to the second problem we did with the opening exercise, I'm paging back right now, you'll see that we found tan theta equals 7 square roots of 2 over 8. We got the same answer. So the Pythagorean identity is our main focus for learning today. And also the fact that tan theta equals sine theta over cosine theta. Cool? Awesome. That's it.